Hi, welcome back to my channel. Well, in this video we'll try to learn some of the basic concepts which are involved in a very important statistical procedure that is known as correlation. We will try to see what are the different types of correlation, how we can quantify the value of this correlation, and how we can explore the amount of association that exists between quantitative variables. So let us proceed. How we can explore the association between two quantitative variables? Well, an association exists between two variables if a particular value of one variable is more likely to occur with certain values of other variable. For example, for higher levels of energy use, does the carbon dioxide level in atmosphere tend to be higher? If so, then there is an existence of association between energy use and carbon dioxide level, which might be of two types: positive association or negative association. In case of positive association, as one variable goes up, another variable tends to go up also, or as one variable moves in one direction, the another variable also moves in the same direction. In case of negative association, as one variable goes up, another variable tends to go down, or we can say in this case the variables move in opposite direction. Now, how can we explore the relationship between two quantitative variables? We can explore the relationship graphically or numerically. From graphically, we can construct a scatter diagram, but numerically, we can explore the relationship by calculating two of the important statistical procedures. One is correlation and another one is regression. Correlation and regression analysis are two statistical procedures which are used for analysis of relationship between quantitative variables. We measure the association between two variables, particularly the linear relationship or linear association between two variables, by means of correlation, and the functional relationship of one variable with other variables by means of regression. The correlation is a statistical technique that can show whether and how strongly pairs of variables are related. More importantly, it refers to the extent to which two variables have a linear relationship with each other. So linear relationship is very important. This correlation actually measures the linear relationship between the quantitative variables. For example, if we'll take an example of height and diameter of trees. In case of trees, as trees grow taller, its diameter also tends to grow wider. Thus, we can say that these two characters, that is tree height and diameter, they are related, they are correlated. Now, the quantification of linear relationship, because correlation always tests the linear relationship between the variables, the quantification of linear relationship that exists between continuous variables can be measured by a very important coefficient that is known as Pearson's correlation coefficient. It is named after a famous statistician Carl Pearson, who has given this coefficient. That is why it is known as Pearson's correlation coefficient. If we will take an example of correlation, we want to assess the correlation between two quantitative variables. For that, the conventional or the traditional formula is nothing. It is the ratio of the covariance that exists between the two variables upon their respective standard deviation, that is summation xy minus summation x into summation y divided by n. N is the number of observations, then the whole divided by the standard deviation of one variable multiply with the standard deviation of another variable. This Pearson's correlation coefficient always lies in the range of +1 and -1. When there is an exact value of +1, we say it's a perfect positive correlation, and if it is -1, we say it's a perfect negative correlation that exists between two variables. Well, it is a parametric procedure and it is based on some assumptions. The first assumption is that the variables under study are continuous random variables and they are normally distributed, which is very important. The relationship between variables is linear. This is also important. Each pair of observation is unconnected, rather independent with other pairs. Now, important features of this correlation coefficient, which is usually written as small r in case of samples, and we are dealing with, and if we are dealing with the this population, then we used to change this R by means of a row. R, or we can say correlation is, or correlation coefficient is always between -1 to +1. It actually the magnitude, its magnitude actually indicates the strength. If it's more towards the positive, more towards this positive one, say it's a positive correlation or a strong amount of correlation, and in case of negative we can say a strong negative correlation, or we can say a linear relationship. -1 or +1 indicates a perfect linear relationship. We can say a perfect negative correlation, or a perfect positive correlation, or a perfect positive linear relationship. Sign actually indicates the direction, and this is very important. If correlation coefficient is equal to 0, it indicates no linear relationship exists between two quantitative variables. Like in this case, it is a correlation coefficient between two variables x and y. That means, it does not mean that these two variables are not related if the correlation value is 0. It means they are not linearly related. They don't have a linear relation. They might be related to each other by some other means. The correlation coefficient is independent of units of measurement. Now, how we are going to test the significance of correlation coefficient? We will use a traditional t-test, and it is equal to r multiplied by under root of n minus 2, and it divide by under root of 1 minus r square. Here r is the correlation coefficient between two variables, and it always follows n minus 2 degrees of freedom. Here the null hypothesis is that there is no correlation, or we can say there is no linear relationship between two variables, and the thumb rule is we have to reject this hypothesis if the calculated value of this t-test is greater than this tabulated value. So under that circumstances, we used to reject the null hypothesis that there is no correlation between. We conclude that there exists a linear relationship between the variables under study. Now, this is a scatter diagram approach of correlation. When we have this type of trend in our graph between two variables which are quantitative in nature, we say it is a positive correlation. That means as x increases, y also increases, or we can say as one variable increases, another variable also increases. And in this case, clearly as is indicated by these dots, as the value of x increases, the value of y decreases. And in this case, as x increases, there is no effect on y. We say there is no linear relationship between the variables. Now there are another three important types of correlation coefficients. One is partial, another one is semi-partial, and the third one is multiple correlation. Partial correlation, actually it measures a linear relationship between two variables while controlling the effect of one or more variables. If I will take an example of this R12.3, it means it shows a linear relationship between first variable 1 and variable 2 controlling the effect of 3, and the formula is this. This is the correlation between first variable and second variable. This is the correlation between first and third, and this is the correlation between second and. So if we have three variables and we know what type of what is the value of the correlation between all these three variables, we can get the partial correlation also. Then there is another type that is known as semi-partial. Semi-partial means the linear, it actually measures a linear relationship between variables. If we have three variables, it measures a linear relationship between x1 and x2, holding x3 as constant for just x1 or just x2. So if we will write it like this, R1 and within these brackets we will write 2.3, it means semi-partial correlation between variable x1 and x2 where x3 is constant for x2 only, and the formula is here that R1 and within this bracket we will write 2.3. It means it measures the semi-partial correlation between this x1 and x2 where this x3 is constant for only the second one. And there is another important correlation which is usually used in case of regression. When we will start a lecture of regression, we will try to give a detailed discussion about this, but it measures a linear relationship between a one variable with a group of linear combination of other variables. And in this case we used to have two types of variables. One is dependent and we have a set of independent variables, which is usually used in case of regression analysis. So we have an example. For example, from a walnut field, 12 plants were selected at random. The length of branch in centimeters, and the number of nuts per branch of the selected plants were recorded. So our y variable is number of nuts and the length of the branches. So results are given in the following table. Then we have to calculate the correlation coefficient and its testing. So we have to see whether there is an existence of linear relationship between length of branch and number of nuts, and if it is positive, then we can say as the length of branch increases, the number of nuts per branch also increases. So for that we have a data set. One is this 12 observations. This belongs to the first variable, that is the length of branch, and this y represents the number of nuts per branch. So how we have to do the analysis, or we can say the manually, for that we have to do the squaring of every variable individually. Each and every point observation has to be squared. Then we used to do a cross multiplication of the first variable with second variable, and the first thing is use the basic arithmetic operation, get the sum of both variables. Summation x is the total of length of branch. This is the total of number of nuts per branch. Then what we have to square each and every observation at the same time. We had to add them. Then put these all values in the formula of correlation, and in this case we have got a correlation value of 0.95, which is positive and more closer towards 1. We can say there exists a positive correlation or linear relationship between these two variables. That means as the length of these branches increases, the number of nuts per branch also increases. But we need to verify whether this value is significant, or whether there is an existence of significant relationship between these two variables, or whether this relationship or this 0.5 is is a real value or it is by chance. For that we have to use this traditional t-test, and we will apply this. This is nothing, this is r under root of n minus 2 whole divided by 1 minus r square. We'll put this value here. Then we have a calculated value of 9.6, and it's the critical or tabulated value for 10 degrees of freedom, because we have 12 number of observation, that is, and because it follows n minus 2 degrees of freedom, that means 12 minus 2 is 10, and the tabulated value at 5% level of significance is 2.23, and the thumb rule is whenever the calculated value of a test of significance is greater than its tabulated or critical value, then under those situations or circumstances we have to reject the null hypothesis. The null hypothesis in this case is that there is no linear relationship between these two variables, since our calculated value is greater than its tabulated value. So we will reject this null hypothesis, and we conclude there exists a positive and significant correlation or linear relationship between these variables. So this correlation is widely used whenever we are interested to seek the linear relationship between the variables that are under study. The only problem with this type of statistical tool or measure of association is that it only measures the linear relationship, and there is no identification of cause and effect. We are not in a position to see the cause and effect. We are not in a position to identify which one is dependent and which one is independent, and it always measures a linear relationship. Because in case of biological phenomena, we used to have always encounter with a non-linear relationship. For that it is not used. For that we have to use regression analysis. So in next video we'll try to explore what are the basic concepts which are involved in regression analysis. Hope you will like this video. Thank you very much.